So to get this to the nearest 16th of an inch, 0.779 over 1. We just turn it into a very simple fraction like that. Then what are we going to do to it? Heard someone try to say it there. What is it? Right now we have a denominator of 1. We want it to be 16. So how do we change that? Multiply by 16. There we go. I heard somebody whispering it in the back of the room, but so 1 times 16 is 16. Now our 0.779 times 16. $12.464, good. Now remember, what that's telling us is that this is between 12/16 and 13/16. Which one is it closer to? The 12, right? Are we going to leave it as 12? (12/16). Remember, the main reason for doing this is if most likely looking for a drill bit size or some sort of tool size, or trying to measure it on the tape measure. We don't have a 12/16 tool in our tool set because they reduced their fractions. That could both be reduced by 4 to give us 3/4. So even though we're going to the nearest 16th of an inch, we can still reduce it if we can there. So that 3/4 is to the nearest 16th. It's just in a reduced form. Okay, for number 2, what do we do with the 4 here in front of the decimal point? Don't be shy today. We leave it, good. So now then, take the 0.398 over 1, and then what? Multiply it by 16 again, good. So 1 times 16 is 16. 0.398 times 16 is 6 point something. There we go, 6.368. So now this is telling us it's between which two ones? Okay, 6/16 and 7/16. And you're right, it is closer to the smaller one, the 6/16, and that of course will reduce. Both of those divide by 2 to get 3/8. So 4 3/8 inches. How many of you had both of the first ones right? Good. Does anybody have any questions on how to do those? Okay. Anybody, how many of you need another minute to finish the last two? Okay, I'll give you one more minute here to take a look at them, and then I'll probably hit it in about 30 seconds for you. Okay, looks like a number of you are done. Let's see how you've done so far and what you have done at least. So for number 3, you guys walk me through it. Somebody tell me what to do first. Leave the 2, good. Then what? Perfect, 0.589 over 1. Make sure we leave the decimal point in it for now. Then what? Careful. 32, good. I knew I'd catch somebody on that one. Okay, so 1 times 32 is 32 for my denominator. 0.589 times 32 is 18.848. Good, thank you. And again, it's always easier for me to think of what it's in between. That's between 1830 seconds and 1930 seconds. The 8 is telling us it is closer to 19. Good. So that's 2 and 19/32 of an inch. For number 4, let's do it backwards here. What'd you get for an answer for number 4? 10/32. Of course, that would reduce to 5/16. Let's go through that. There's no whole number, so we're just going to take our decimal over 1. Times 32 on top and bottom. Gives us a denominator of 32. 0.308 times 32 is
9.856.
9.856. And of course, that is between 9 and 10. Definitely closer to 10/32, giving us 5/16 of an inch. Good job. Okay, so last class we spent our time doing operations with decimals, converting the decimals to fractions. This to me is one of our more important conversions, going from a decimal into a specific type of fraction for our measurement. If you recall, we did take decimals like 0.738 inches and convert them into exact fractions. How would we do that for this? Well, 0.738 is 738 what? Tenths, hundredths, I heard someone say it there, thousandths, good. So it's 738 thousandths. Remember, we discussed our decimals are nothing more than an abbreviated way or a shortcut way of expressing fractions that have those denominators that are powers of 10. So 738 thousandths. Of course, we wouldn't leave it like that as a fraction. We would reduce it. Both can be divided by what? $32? Can you divide that by 1,000? I don't think divides by 32. Not quite going to work for us. Okay. That's okay. If you're not making mistakes, you're not trying, right? They are both even, so we can divide by 2. 738 divided by 2 is 369, perfect. 1,000 divided by 2 is 500. Now looking at these, I know that this can't be reduced only because I know that 500 is really only divisible by 2's and 5's. And 369 is not divisible by either of those. How do I know that it's not divisible by 2? Yep, the last digit's 9, that's an odd number. How do I know it's not divisible by 5? Perfect, doesn't end with a 5 or 0. Just at a quick glance, can anybody tell me what 369 does divide by? If we add up digits, 3 plus 6 is 9, plus 9 is 18. So it'd be divisible by 3, and actually by 9 as well, but 3 is the important one. So that cannot be reduced. Why is it that when we're dealing with construction applications that we would not want to be exact? I mean, this is the exact fraction for the decimal of 0.738. Why is it that we prefer these over this? Well, I kind of alluded to it a few minutes ago. Where do you find that on the tape measure? You can't, no. Somebody said 3/4, and that's probably what it would round to, is probably 3/4 on your tape measure, depending on how exact you're going to be. Okay, with that, let's take a look at some of our applications then of our decimals. One application I want to look at is we're going to do a beam buildup. So for our beam, we're going to use 1 3/4 inch LVLs. LVL stands for laminated veneer lumber. So 1 3/4 inch means they're 1 3/4 inches wide. So what we have is we have a wall that is 5.5 inches wide total. We are going to use 3 of these LVLs to build a beam that sets in that wall. I have to redraw my wall. We've already discussed my lack of artistic talent. There we go. Now notice I left space between the beams, the LVLs. The reason for that? How much would 3 LVLs cover? Well, we're going to do this. We're going to convert them to decimals. 1 3/4 is 1.75. 5.5 is going to be what is a decimal? Come on, you know it.
5.5.
5.5, thank you. So with them in decimal form, how much is 3 of those LVLs going to cover? What would the width be if it was just those 3?
5.25.
5.25 inches. Good. So the 3 LVLs cover 5.25 inches. But we need 5.5 inches of thickness. How much more thickness do we need for that beam to fit exactly inside that wall? 0.25. Good. 5.5 minus 5.25. We had to add our 0 here to fill in that missing decimal place. And we subtract. 0 minus 5, we have to borrow. That'll be a 5, and this will now be a 10. 10 minus 5 is 5. 4 minus 2 is 2. So 0.25. I'm guessing that many of you were able to do that in your head because you saw the halves and the quarters, and that's good. Now, here's the catch. I don't want to just use one piece of plywood to fill in. I want this beam to be uniform. So I want to split up the filler. I'm going to take 2 pieces of plywood, one in this joint and one in this joint, to fill that up. So how thick does each piece have to be? 12 point, I heard 12.5. You got the right idea there. It's just the decimal point's in the wrong spot. 0.125. Perfect. So let's walk through that calculation. 0.25 divided by 2. Does 2 go into 0? No. Before we can move on, of course, we move up our decimal point. We can't pass our decimal point without doing something with it. Does 2 go into 2? 1 time, right? 1 times 2 is 2, and there's nothing left over. What do we do next? We bring down the 5. 2 goes into 5 how many times? Twice? 2 times 2, well, 2.5, yeah. 2 times 2 is 4. We have 1 left over. We're out of digits, so what do we do? Add a 0. Well, if we have a decimal, it's kind of hard to put in a remainder because we don't know really what value it would be back there, do we? We can add zeros and bring it down. 2 goes into 10? 5 times, and that's exactly it. So nothing left over. So 0.125. Now this is a case of a problem that might have been easier to do as fractions because you would have had the 1/4, and from there dividing that in half, it's easy to see it has to be 1/8. And I'm hoping you guys, as we go through the semester, are getting good at working with those fractions like that. So anyway, let's look at one more example here with our decimals. We're going to look at a piece of pipe here. Pipe can be measured in one of two ways, ID and OD. ID stands for inner distance or inside diameter. You got it. OD stands for outside. Very good. Was that a guess or did you know that from before? Okay. So for this pipe, we have an outside diameter, an OD, of 1.875 inches. And there is a wall thickness of 0.1875 inches. I want you to find the inside diameter. So go ahead in your notes and find that quick. How would we approach this one? Or how did you approach this one, I should say?
First, I doubled the 0.1875.
Okay, so we double the 0.1875, which gives us 0.375.
No.
Then what?
Subtracted that away from the 1.875. Now 1.5.
Perfect. So we take the 1.875 minus our 0.375, and we get 1.5 inches. Good. So the beauty of the decimals, of course, is your calculators work wonders. You don't even have to know anything special about entering them. As I mentioned in last class, though, be careful, because like I said, that decimal seems to be the one button on that calculator that causes errors the most, so be very careful with it. Make sure you have an idea of what you're expecting before you blindly punch in numbers with it. Okay, so next, we're going to take a look at a floor-to-ceiling dimension that is given as 109.5625 inches. And we have a beam that has a depth of 11.375 inches. On the bottom of that beam, there is a plate. This plate has a thickness of 0.425 inches. There's a post going from that plate down to the floor. And on the floor there is a plate. This plate has a thickness of 0.485 inches. This occurs a lot. The purpose of the plates is to keep that post on top, to keep it from digging into the beam. And metal to wood is generally a bad connection. So if you have that end of that post into that beam, it can actually deteriorate the wood quickly and it actually settle into the metal quite quickly. You end up, I've seen them with as much as 3/8 of an inch in about 15 years of penetration into that wood and causing the beam to sag. Same on bottom. Wood structures tend to shift. So shifting in the wood up top here causes that post to wiggle slightly, and slight movements of metal on concrete cause the concrete to actually slowly be abraded away, to be worn away by the metal. So that plate on the bottom allows the post to slide on that metal without digging into the concrete. So what I'm asking you to find here is what is the exact length that that post has to be. 97.2775 inches. Somebody knew where I was going with that one, huh? Okay. How'd you go about finding that? Okay. Perfect. And that's one way to go about it. You could take the 109.5625 and subtract each of these decimal amounts. So when I subtract the 11.375, I've got 5, 512, this is going to be 7, well here 4 and 15, that'll be 8, 1, 8, 98.1875. Then we'll subtract the 0.425. Putting in the 0, we've got 5, 2, 6. Borrow from the 8 to make it a 7 and 11. 7. So 97.7625. And then we subtract the 0.485. Putting in the 0, so we got 5. Borrow from the 6, that's 5 and 12. 7, borrow from the 7, that's 6 and 15. 7 to 97. So yes, 97.2775. Did anybody go about it in a different way? Perfect. Some people are better at addition than they are subtraction. Another thing is subtraction can only use two numbers at once. Addition, we can add multiple numbers, so it can be slightly quicker depending on what you prefer to do. 5, 5, and 5 is 15, so carry the 1. 1 and 7 is 8, 10, 18, carry the 1. 1 and 3 is 4, 8, 12, so 2. Bring down my decimal point and carry the 1. So we get 12.285. If we subtract that from the 109.5625, we'll get the same answer. Okay. Now let's look at one more example here. Let's say that we have a stack of plywood that is 13.5 inches tall. So it's stacked this way. 13.5 inches tall. You look at the top sheet and the label says that it is 3/8 inch thick plywood. How many sheets are in that stack? I'm going to give you a minute to take a look at that, see what you come up with. I'll give everybody else a minute to come up with it, see if you guys can come up with the same answer. Okay, so we have decimals, 13.5 inches here, and a fraction of 3/8 of an inch. One of them has to be changed. We can either change 13.5 into a fraction or 3/8 into a decimal. Very easy to turn 13.5 into a fraction. What would it be? 13.5. Good. As I mentioned before, if you're working in construction, you're going to get to know halves, quarters, and probably even the eighths as a decimal to recognize them quickly. So you could do 13.5 divided by 3/8. Our other option would be to change 3/8 into a decimal. What's 3/8 going to be? you divide it out, 3 divided by 8 gives you 0.375. So that would have been 13.5 divided by 0.375. Either way, they do give you 36, so it's 36 sheets. Something I want to note on this one, however, either way you do it, I'm going to write it out as a decimal here quickly. It's 13.5 inches divided by 0.375 inches. We said before that when you multiply numbers, you combine the counts, and then you also combine the names. We had something like 2.3 inches times 4.1 inches. If we do 2.3 times 4.1, we're going to get 9.43. Well, what's my label on that going to be? Inches squared. We also combine the names. Inches times inches make inches squared. Well, division follows the same rules as multiplication. So when we divide, we do divide the numbers. 13.5 divided by 0.375 to get 36. But we also divide the name. Well, inches divided by inches, anything divided by itself cancels out. So there are no units on this number. 36 has no name. It is just a count or an amount. It's 36 sheets in this case. What's that? Okay. Let's take a look. Let's say we dug a basement, and overnight we get a lovely little rainstorm. So we go to pump our basement out. That box is my version of a pump. So let's say we start this pump in the morning. This pump can pump 7.8 CFM is cubic feet per minute. After we set up our pump, we go to grab another pump that's larger. We set that one up and start pumping. That pump is capable of doing 13.9 CFM. Our first pump runs for 6 hours. Our second pump, because we had to run and get it, runs for 4.5 hours. How many cubic feet of water were in our basement? Well, rather than having you do this one on your own, let's just have you talk me through it. So to do this, I have pump A and pump B. I have whatever was pumped by pump A plus whatever was pumped by pump B is going to give me my total. How do I find the amount of water that was pumped by pump A? Not 60, but just 6. Is that going to work? No. Where'd you get the 60 from? Okay. You were doing that conversion. Okay. I thought after I said no that was where you were heading with that. If we look at this, 7.8 cubic feet, so that's feet cubed per minute, can be set up as a fraction like that. Our units, or our labels on our dimensions, work just like the numbers do. Those fractions can cancel out and all of that for us. The 6 is in hours. That does not match up with our minutes. So we have to do something to turn it into hours first. So if we do this, 60 minutes in 1 hour, 60 minutes per hour, what that does for us is it converts this from cubic feet per minute to now cubic feet per hour. 7.8 times 60 is 468. This is now cubic feet per hour. Are we done yet? No, we still have to account for the fact that there were 6 hours. Now, at this point, you guys have said we're going to multiply, but if we're not sure of that, the units can actually tell us. We want to know, or we want our answer to be cubic feet, which means we have to get rid of hours. Since hours is on the bottom of a fraction, the way we would get rid of it is to multiply by a fraction that has hours on top. Well, we would then just multiply by the 6 hours. The hours will cancel out. We could call that 6 over 1 if you wanted to, but we don't need to. 468 times 6 is 2,808. And since the hours canceled out, the only units we're left with are cubic feet. Now, after we've done it with one of our pumps, we can do it with the other one. We don't have to go through the units to analyze what we're doing. We're going to take our 13.9 cubic feet per minute, and how we're going to convert that to cubic feet per hour. Times 60, right? 13.9 times 60. 13.9 cubic feet per minute is 834 cubic feet per hour. What are we going to do with that now? How long was that pump running? 4.5 hours. Good. So we're going to multiply by 4.5 hours. So you can see the hours would cancel out. So 834 times 4.5 is 3753 cubic feet. So we're just going to add those two up. In this case, we're adding whole numbers now. So 3 and 8 is 11. Carry the 1. 1 and 0 and 5 is 6. 8 and 7 is 15. So 5 carry the 1 and 6. 6,561 cubic feet of water. To give you an idea, the conversion is 1 cubic foot equals 7.48 gallons. So a little foreshadowing to our measurement coming up in a couple of weeks. If I have 6,561 cubic feet, to turn that into gallons, am I going to multiply by the 7.48 or am I going to divide by the 7.48? Well, to figure it out, we do this. 6,561 cubic feet times, we're getting rid of cubic feet. So to get rid of cubic feet, I'm going to put cubic feet on bottom so that they will cross cancel out in our fractions. So gallons go on top. So our units are 1 cubic foot equals 7.48 gallons. When we talked about fractions, we talked about unity fractions. That's one of them. It doesn't look like it, but that equals 1. The denominator and the numerator both have the same value. 1 cubic foot and 7.48 gallons are the same thing. But now what this shows us is our cubic feet will cancel out, and it is 6,561 times the 7.48. So that is 49,076.28 gallons. That's a lot of water. What's that? Yeah, that would be a pretty heavy rainfall, that's for sure. Well, I mean, a lot of people underestimate the volume of water. Any of you have a swimming pool in your backyard? Okay, like a 15 foot or a 16 foot? All right, let's do this. Since I don't want to get into area circles right now, let's just do 14-foot square. A 14-foot square pool is approximately the same size as a 15 or 16 foot, well, 16-foot round pool. So that's going to give us an area of 14 times 14, or 196 square feet. Those pools are usually either 4 or 5 feet high. So let's say that it is 4 feet tall. So 196, I don't know why I put squared like that. 196 square feet is the area of my bottom, times 4 feet tall is going to give us 784. Square feet times feet is cubic feet of water, times 7.48 gallons per 1 cubic foot. You're looking at almost 6,000 gallons of water just in that little swimming pool. So if you think of that, this is only 8 times that amount of water. So a big house foundation could easily collect that amount of water in a heavy rain. Okay. Let's look at some other applications of our decimals. In fact, what I want to look at now is some other operations. We've looked at addition, subtraction, and multiplication and division. There are 2 other main operations we want to look at out there. We've already discussed a little bit what that means. That means 8 squared. How would we calculate it? Eight times 8, right, for 64. So if we have 0.8 squared, what are we going to get? We want to jump out to say 6.4, but it actually comes out to be 0.64. Eight times 8 is 64, so 4 carry over the 6. But then you look at the decimal places. Remember, 1, 2, we have to have 2 decimal places in our answer, 0.64. Part of the confusion is that's smaller than what we started with. When we square something, don't we usually get a big number? When we squared 8, we got 64. It got a lot bigger. Well, let's look at our multiplication for just a second. If I have something like 4 times 3, I get 12. When I multiplied by 3, it got bigger. But if I have 4 times 0.5, I'm going to get what? 2. When I multiplied by 0.5, I got something that was smaller. Why is that? Well, what's 4 times 1? 4. Anything times 1 is itself, stays the same. We're used to multiplying by numbers that are bigger than 1, like our 3. So we're used to multiplication making things larger. But if we're multiplying by something smaller than 1, we're going to get something smaller than what we started with. So for powers, we're used to powers making things really big. I mean, 2 to the power of 8 is 256. That gets big really fast. But if the thing we're taking to that power is smaller than 1, each time it multiplies by itself, it's going to continue to get smaller. Without punching into your calculator, let's look at this. 0.2 to the power of 8. Well, we know 2 to the power of 8 is 256. So we know that 256 plays into this somehow. The question is, how many decimal places? Well, this is 0.2 times 0.2 times 0.2 times 0.2. I'm not going to write them all out. But each 0.2 has how many decimal places in it? 1. And how many times are we going to have it here? 8 times. 1 times 8 makes 8 decimal places. So if there are 8 decimal places in the problem, as we've said before, there has to be 8 decimal places in our answer. So that is 0.0000256 to give us 8 decimal places in the answer. If you look at that, you might see 1 decimal place in our number to the power of 8. You took the number of decimal places times the power to get the number of decimal places in your answer. So if I have 0.15 to the 3rd power, how many decimal places is that going to have in the answer? There's 2 decimal places in the problem, in the number. To the power of 3 means we're going to have 2 times 3 will give us 6, right? Because we're going to have those 2 decimal places 3 times if we multiplied that out. So now 15 to the power of 3 is 3,375. So 0.15 to the power of 3 is 0.003375. Any questions? Okay. Go in the other direction then. Now we've talked about the opposite of a power is a root. What's the square root of 0.4 going to be? Will it be 0.2? Most people want to jump on that. But if I square 0.2, 2 times 2 is 4, and I have to have 2 decimal places. So 2 squared has to be 0.04, and not 0.4. When we square root it, if it's going to work out evenly, it'll cut the decimal places in half. The square root of 0.04 would become 0.2, half as many decimal places. The square root of 0.25, will that work out to be 0.5? Well, is the square root of 25 5? Yes, it is, right? But this goes from 2 decimal places down to 1, so that's going to work. So back up to the square root of 0.4. We have really no option to do that except to use our calculator. So that is 0.6325 if we round it. Now I said we have no option but to use our calculator. There is an algorithm to allow us to calculate square roots by hand. You guys would have to make me pretty angry to show you that. It's not a pleasant algorithm. Has anybody ever seen it? No? Okay. It really is not a pleasant algorithm. Is anybody terribly curious to see how it works? All right, a couple of you? Oh, sure, you're going to make me remember how to do it. Okay, let's see if I can do this. Somebody give me a 5 or 6 digit number. A million? It's better if it has what's that? 11,347. Okay. Here's what I'm going to do, is I'm going to start at my decimal point, and I'm going to group the numbers 2 at a time. So the 4 and 7 go together, then I'll leave a space. The 3 and 1, I'll leave a space, and then the 1. I'm just grouping them together in pairs. And now I'm going to take my square root. I start out with my first set here, which only has the 1 number in it, 1. And I find the largest number that when squared will go into that. Well, 1. 1 squared is actually exactly equal to 1. So I do 1 squared, gives me 0. So that works out nicely. Now I bring down my next pair of numbers. So I'm dealing with 13. This is where it gets pretty dicey. I take what I currently have for my answer, in this case 1, times 20, which is 20. So in my next step, hopefully none of you are writing this down. In my next step, I'm going to take 20, and the formula is plus x and times x. So what that means is the next number that's going to go up here has to make this work so that it's smaller than 13. Well, is that going to work? Well, there's nothing I can put in there, is there? If I put, well, I can put in 0. If I put in 1, 21 times 1 would be 21. That's bigger than 13. So the only thing I can use is 0. That would be 20 plus 0 is 20 times 0 is 0. So I get 13. Bring down the next pair, 47. So now I've got 1,347. What I have up here now is 10. So it's going to be 10 times 20 is 200. So I'm going to now use it's 200 plus x times x. Well, that's going to go in there. Now I'm thinking I'm going to try 6. So that would be 206 times 6. 206 times 6 is 1,236. That's going to work. So this next digit here is going to be 6. So let's subtract. It's a 1, and a 1. Now after the decimal point, I can keep going, but instead of adding single zeros, I have to add pairs of zeros. So now I bring down that pair of zeros. Now I have 106 up here. It's 106 times 20, which is, what, 2,120? Question? Okay. Yeah, what is it? Okay, so 2,120 here. So now it's going to be 2,120 plus x times x. I have to go into 11,000, 11,100. Let's try 5. If it was 5, that'd be 2,125 times 5, which is going to give me, what, 10,625? Which will go in there. So 5 is going to work. Now I'm going to stop there. Right now I'm at 106.5. I'm just going to see if I did this right. Second square root of 11347. 106.5, and then it would keep going from there. Now as you can see, that is really no fun. I maybe do that calculation once or twice a year just to prove I can. Otherwise, the calculator is a wonderful tool for doing square roots. Okay, so to wrap up our decimals for now, let's take a look at a problem like this. I want you to try this one in your notes quick. It's simply an order of operations problem. The difference is we now have decimals in there instead of whole numbers or fractions. See what you can come up with. I'll give you a few minutes. Anybody have an answer for me? Don't want to be brave? Let's take a look and we'll see if you agree with what I got. This here is a fraction bar, and it is an enclosing symbol, which means we're going to have to start with this first. And it tells us we have to do what's on top first, then do what's on bottom, and then divide. So on top, what do we have to start with? Parentheses, enclosing symbols, right? So in there we have to do 12 times 0.4, which is going to be 4.8. Now this one's a little different. What do we have to do before we can get rid of the parentheses? We have to do the exponents. We have to do the power. 4.8 squared is 23.04. So now the parentheses are gone. We squared them. We got rid of them. And all that's left is adding. 18.54 plus 23.04 is 41.08. So the top of my fraction is 41.08. Or not 08, 58, sorry. Come on. How many of you had 41.58 on top? Just a couple of you? So we lost you already on that one? So now we have to do the bottom. What do we have to do first on bottom here? Square root. Square root of 2.25 is 1.5. Next, we have to do 68 times 0.08, which is what? 5.44, I believe. We subtract 1.5 to get 5.44 minus 1.5 is 3.94. So we have 41.58 on top, 3.94 on bottom. Now I left a space here. Why did I leave that space? Don't forget about the 9.6. 9.6 plus whatever that result is. What do we have to do next? We're going to divide. Good. Now I'm going to round to 4 decimal places here. That's going to be 10.5533. So we have 9.6 plus that. 9.6 plus 10.55 is going to be 20.1533. Did anybody come up with that? No? Okay. I'm not going to be quite that mean to you on a test or quiz, but I mean, it's a problem that, with the help of the calculator, probably could get just by going through the steps of the order of operations. How many of you think you would have got it if I'd have given you a little bit more time? Not a lot of confidence in it? Okay. Like I said, I knew I was stretching that one a little bit when I put it up there. Now, another application of decimals that I want to make sure we go over is a transit. Now, transits can be read in a couple of different ways. Well, not read in a couple of different ways. Transits are always read in the same way. It's the stake that we're using that we have to look at the different scales. But what a transit is, it's almost like a scope like a telescope or whatever, and it has bubbles on it so you can get it perfectly level. And then once it's perfectly level, you have a measuring stake. How many of you have ever used a transit? Anybody? Nobody? Okay.
We seen one yesterday when we visited a job site, but they weren't using it. We just got a visual.
Okay. Well, then it's perfect timing. You've at least seen what it looks like. So what you do is you take this stake, and it's just like a big plastic rod. It's like a telescoping rod, almost like an antenna for a radio that you can pull up and telescope up and down. So you pull that up, and on that rod, it's labeled. Now this might be labeled 56 inches, 57 inches, 58 inches, and so on. Now it can be labeled in a couple of different types. It can be labeled like this in inches, and generally between the inches it is done in tenths. So you get 56.1, 56.2, 56.3, and so on going up. Or it can be labeled in feet, and between the feet it's divided up in tenths and hundredths. And we'll show you that in just a minute. So anyway, if we read this, let's say we look at this here, we look through our scope, and on the stake here, we get a reading of 68.4 inches. What that is telling us is this ground here is 68.4 inches below the level we set our scope at. And we always have some sort of a reference point. So let's set that as our reference point. When we go to scope out this spot on the ground right here, that's obviously higher than the previous place. So when I look through my scope at my scale here, since this point is higher, do I expect that number to be larger or smaller? Your instinct is to say larger, but remember, what we're measuring is the distance from the scope down to that point on the ground. If this is a higher point, the distance is going to be less. This will be smaller. This might be, if this were, let's say this were 6.7 inches higher, this reading would be 68.4 minus 6.7, or 60.7 inches is what that reading would be when you look through the scope. So let's look at this. Let's say you are setting forms for a floor. And in the middle of the floor, there's a drain. The level of the drain is to be 1.6 inches below the level of the walls. So you set up your scope. Now for something like this, you could set up your scope in the middle of the floor somewhere, or outside of a door if you've got a spot where you can get it in line with the drain. So you set up your scope, and you put your stake on the edge of the wall, and what it reads is the level of the concrete at the wall is 47.8 inches. What reading do we need then to set up our drain? When we move our stake over here, what do we want this to read to have that 1.6 inches below the wall, the concrete at the walls? What's that? Okay, first instinct is to subtract, isn't it? But is this number going to be larger or smaller? You went smaller by subtracting, but it's going to be further down, isn't it? 47.8 plus the 1.6 will be 49.4 inches is where that level is going to be. So that's what we need to read. Now, I'm actually glad you made that mistake, because I've seen some very experienced concrete contractors make that very same mistake. They get into a hurry. In fact, this exact example was a job I did up by Cumberland several years ago. I was doing outside work when the concrete contractor came in to do the floor in the milk house. They knew that the drain was supposed to be 1.5 inches below the level of the floor at the walls. They set the transit up, they read the scope, read the scale, subtracted 1.5 inches, set the drain pipe where that height was going to be, and poured the concrete. And guess what? the top of the drain was the highest point in the floor. So there was obviously a jackhammer involved. Very easy mistake to make. So let's say I have 4 scope readings. I have point A, or 4, we'll go 3, A, B, and C. These scopes usually only have a line going across them. And let's say that for point A, look at our stake, and we see this is 58. For point B, we look here and we see that this is 54. And for point C, this is 52. Which of these points, A, B, or C, is a higher point? Now the scope is staying in the transit's staying in a single spot. Which one is the highest point of the 3? C, very good. If we have our scope set up, I know it is confusing, isn't it? Point A is 58 inches below. Point B is 54 inches below. That's A. That's B. Well, technically it's actually, what? This is 58.3. This is 53.8. And this is 52.2 inches below. So it's less distance below, so it's the higher point. Now this is if a transit scope is read in inches and decimal inches. Transit scopes can also be read in decimal feet. For example, let's say we look through the scope and this is labeled a 4 on our stake. I'm going to give myself some more room here. So here's my stake, and let's say I have this bar here that's labeled 4. That is 4 feet. So I'll be above that, I might have something that looks like this. This would be colored in black. I'm not going to color them all in, but I'll do that to just make the effect. That would be labeled 4.1. So what this is here, this is 4 feet to the top of that line. To the top of this line, that is 4.1 feet. So what that is, each of these lines is 0.2 of a foot. But you'll notice the thickness of the line is the same as the size of the gap between them. The reason for that is the bottom of this line is 4.01 feet. It's 1/100th of a foot. The top of the line is 4.02 feet. The bottom of the next line is 4.03 feet. Top of the next line is 4.04 feet. Bottom of the next one is 4.05. Top of this one is 4.06. Bottom of this one is 4.07. Top of this one is 4.08. The bottom of this is 4.09 feet, and the top is 4.1. And in the assignment out of the book for the day, there is going to be a transit reading where they show you a stake, the measuring stake, that is divided up like this. To be honest, if I bought a transit and it came with a surveyor stake like that, I would buy a different stake to use because it's very difficult to read. But there are many of them out there that are like that. Of course, now a lot of them are electronic as well, so that helps. Okay, there is a new quiz for you guys to take today. I cut you guys short again, darn it. Sorry about that. So there is that quiz I'm going to let you guys work on here in class for the rest of the hour. there is also some homework out of the little book. I know. The good news is no class on Friday, right?
That's right.
There you go. So in the little book, Unit 15, do the odds. In the big book, we're going to have you do page 127, which is exercise 3-19. We'll just have you do 21 through 31, the odds. So just a few of the really tough order of operations. Mr. Berghammer, I also got your message about the other quizzes. I just haven't had a chance to print them off yet. I'll get them printed off and scanned to you here in the next couple days.
Yeah, that is fine.
Okay.
This board looks, so I don't feel like it's a big rush, but I just, for one other reason, I couldn't, when I did print them, they didn't have the markings on them, and then.
Yep.
So I'm not really sure.
It all depends on the version of Word you have. If you don't have the same version I do, sometimes the markings just don't show up.
Okay.
So I'll just print them out and scan them in for you. No problem.
I appreciate that.
You bet. You're welcome. Well, you guys have a great day. I'll be on the network here for probably about 10 more minutes before I shut it down for my next class. Like I said, you guys have the rest of the time to work on the quiz and then the homework for over the weekend.
Thank you.
You bet.